And okay, so the third topic is related with investigating properties of lost landscapes. It's the most theoretical one, okay? So this topic is, there's some theory involved, you know, to study. So not only implementation, but there's some, you know, pen and paper work. So, okay, this is like from some time, there's like a lot of critical, there's a lot of criticism about, okay, deep learning. There are two things. Deep learning works very well for some application, for some particular applications, but there's also on the other side, there's a lot of criticism related with issues like lack of interpretability. I even saw a paper called that artificial intelligence is not artificial nor intelligent. So there's a lot of hand tuning, you know, so it doesn't work out of the box, and you even if it works, you don't know why. So these are type of issues that everyone is aware of. And so one research direction would be to investigate, okay, to get some intuitions and some interpretation how deep learning works is to look at the lost landscapes. Okay, so as you know from the course, so to train, when you train a neural network, is basically minimize, you just minimize loss landscape, the loss value. Okay, you have some loss like means MSE, or maybe you have cross entropy loss. You have, you know, prescribed loss that you want to minimize, and the set of weights that you obtain, the minimizer, is the trained network. Okay. So we can look maybe what happens there, yeah? How the loss landscape looks like, because when you run the optimizer, you converge fine, but you don't know where you converge. Do you converge always to the same minimum, or there are like many local minima, etc.? These questions are not obvious, and in practice, what you can see, it can be really wild. Okay, the loss landscape is, so this is taken from a really popular paper about how to visualize loss landscapes of deep nets in low dimension. So they presented some examples, and sometimes the loss surface is really wild. So there's like a lot of values, a lot of minimas. So it really depends where you start your optimization in this space. You can converge to many different points, and moreover, there are like a lot of local minima, okay, which is not good. And you can mitigate this. Okay, some architectures, they have better properties regarding that. And this research area is actually, this kind of touches the art even. If you go to the webpage called Lost Landscape, there's like there's even, you can find art. So people are like visualizing. People are visualizing lost landscapes of deep neural networks in like fancy way, and it looks amazing. There's this movie is taken. There's a software called Lost Landscape Explorer, yeah, which actually allows you to explore the lost landscape. of your neural network. And this, okay, as you see, this is like really complicated structure. And the question, the main question is if there's like how many minima there are. Is there like global? Where is the global minimum? How to find it? Because ideally you want to converge, obviously, to the global minimum. And the question, another question related is if there are like local minima and how to avoid the bad local minima. And there's a lot of, okay, not surprising that there's a lot of research done on that, because it's like extremely practical problem. So the consensus now is that for really big, wide, and over-parameterized networks, so you have over-parameterized, it means that you have much more parameters than data. And then the consensus is that optimizers like SGD or Adam that you know, they will converge towards global minimum, and this global minimum will actually have zero loss. So if you run it forever, optimizer forever, for wide and over-parameterized network, you should see smaller and smaller loss values. Because the optimizer will converge towards global minimum, which attains zero loss. Okay. Okay. However, obviously, not all architectures are like that. That you have, wide. You have a lot of wide over-parameterized layers. One example is autoencoder. You actually implemented simple autoencoder, which had only one single layer. Here we have example of autoencoder architecture which has there's like wide layer, then there's like a really narrow layer, and again this wide, and the input is the same as output. So you train it to find like optimal representation of your data set. So the representation of your data points can be taken from this narrow layer. So, and you kind of say that usually you don't want to have it too wide. You prefer some kind of low dimensional representations. So that's why we use narrow layers in autoencoders. And then, okay, so the theory doesn't apply anymore. And then actually some experimental results show that we have multiple local minima. And the optimizer is not obvious where optimizer will converge to. Okay, sometimes it chooses another better minimum. Sometimes it converges towards bad minimum. And that would be good to understand. So the work is on understanding the properties, So there are many questions, So how many local minima there are, how the loss landscape looks like, how to converge towards global minimum, how to find the global minimum, what type of optimizer to use. Yeah, and this is done for this is autoencoder. Okay, so this is not classification. This is like a typical regression task. So you want to train it. The input is the same as the output. Okay, and you train it to map to represent your data points using this narrow representation from this layer.